Imagine standing at the top of a rugged mountain. A storm rolls in, and you must reach the lowest valley floor as quickly as possible. But there's a catch. You're blindfolded. You can't see the trail, you can't spot the valley, and no map to guide you. Every step is a complete gamble. To survive, you must stop relying on your eyes. Instead, you have to rely entirely on what you can feel right beneath your feet. When an artificial intelligence is first turned on, it functions exactly like that blindfolded hiker. It starts out full of random, untested settings. If you ask it a question, it makes terrible blind guesses. This 3D diagram shows the landscape the AI has to navigate. The height of this mountain represents the AI's error rate, what computer scientists call a cost function. The higher up the AI is, the more mistakes it is making. The goal of the AI is to get off that peak. It needs to hike all the way down to the bottom of the valley, where its errors drop to zero. Since the AI can't see the whole mountain at once, it needs a mathematical sense of touch to feel the shape of its own mistakes. That sense of touch is calculus. Before taking a step, our hiker sticks out their boot, pressing into the ground to feel how steep the slope is directly beneath their foot. This 2D diagram shows a slice of our mountain. The straight line under the point measures the exact slope, a derivative. It tells the AI how to move, taking massive leaps when steep and shrinking steps as it flattens so it doesn't overshoot the bottom. Derivatives take that physical feeling of steepness and convert it into mathematical instructions for the AI. Move exactly this far in this direction. In a real AI model, the path expands into a landscape of millions of variables, balancing things like a user's age, their location, and past purchases all at the same time. On this 3D grid, the AI tests the slope facing north, freezing everything else. Next, it tests the slope facing east. Testing one variable while holding others constant gives us partial derivatives. Merging them creates a single arrow pointing down the steepest path. By combining all these individual measurements, the AI gets the precise, optimal direction to step downward, no matter how complicated the data gets. This repeating loop, feeling the ground, calculating the steepest angle, and taking a step down, is the core engine of machine learning. It's an algorithm called gradient descent. The AI can choose its pace. The deep look approach scans every inch before stepping. It's accurate, but computationally massive. Alternatively, the snap judgment approach skips the map, feeling a random patch to take quick, erratic steps. It bounces around, but navigates the terrain much faster. Picking the right method dictates whether the AI learns efficiently or gets permanently stuck in a false valley. But the AI can't just look down at its boots forever. To know if it is actually making meaningful progress, it has to measure how all those tiny steps add up over time. This visual shows integral calculus, the mathematical partner to derivatives. Instead of measuring immediate steepness, an integral calculates the total volume of the space under the curve. It tells the AI the total sum of the errors it has made throughout its entire journey. By measuring this total volume of error, researchers can see how stable the AI's learning is. It acts as a high-level report card, showing whether the model is actually settling into the bottom of the valley or just bouncing around in a massive pit of mistakes. If we scale this up, we see a massive interconnected web of millions of hikers moving across the mountainside together. This web is a neural network. Because everyone is tied together, if a hiker at the very front of the pack makes a misstep, they have to send a signal backward down the ropes to warn everyone else. Watch this network of nodes. To correct the group's path, the AI uses a concept called the chain rule. The chain rule sends that error signal backward through the entire system, calculating exactly how much each individual node needs to adjust its own position. Because of that rule, millions of artificial neurons can shift their footing at the exact same time, correcting the entire network's path based on a single collective goal. Eventually, the ground flattens completely. The cost function drops to zero. Our hiker has found the lowest valley and finally pulls off the blindfold. The AI is fully trained. When an AI predicts your next word or generates an image, it is easy to feel like it has a biological brain that's actually thinking. But there is no magic inside the box. It is an incredibly fast machine executing precise mathematics. Every seemingly intelligent action it takes is just gradient descent, using the tools of calculus to feel its way down the mountain.